Hey guys, welcome back to another video. Today we'll be taking the course structural mechanics and we'll be calculating reactions as well as shear force and bending moments diagram. Please stay tuned. So for this beam, it has a pin support and a roller support, and then it also overhangs to a 10 kilonewton load on the right hand side. It also has a uniformly distributed load. So we talked about the types of loading and the types of support in our last video. So in this video, like I said, we're going to be calculating the reaction, the bending moment, and the shear force diagram. So first of all, we want to draw the free body diagram. So have a beam. Don't mind my drawing. I have a beam of a 10 kilonewton load here. So assuming this is side A and then this is side B, have a reaction RAY in the vertical direction and RAX in the horizontal direction. We also have one here. No, sorry, it's here. RBY. Then we have our UDL. And they said this is 12 kilonewton per meter. So after drawing our free body diagram, the first thing we want to do is to take moment. So where are we going to take our moment from? To know where we're going to take our moment from, you're going to look for the site most times with two or more unknowns. Two unknowns. So we have RAX here as an unknown, RAY as an unknown. So any place we are taking moments from, all the forces acting on that point is equivalent to 0. So if you take moments from about A, taking moments about A, as we're taking moment about this side. So all the forces acting on this point is equivalent to 0. So let's put our distance. We have 4 here, 4. We also have 3, right? All right, so take moment about this. So we definitely want to turn this our UDL to a point load. So what do? What's the trick? The trick is that if you have a UDL like this, it's like a triangle, right? You take the area of this shape, and usually this 12 kilonewton is usually the base. 12, then times length. The length is 4. So length times breadth, like the area of a triangle, that's 12 times 4. That's going to give us 48. So we have that. We have a 48 kilonewton here. 48. And it's acting where? It will act in the middle, because that is where it would be a triangle. So it will act is a rectangle rather. It's act in the middle. So we have 2 here. 2, 2. Right? Alright, so take moment about A. We take from this one. I always like to say my clockwise moments are positive. You can decide to say if your clockwise movement are positive, that means your anti-clockwise be negative. You can also decide to say, my anti-clockwise, I want it to be positive. That means your clockwise is going to be negative. All depends on the orientation you wish to follow. So we are going to be taking clockwise. Let's disregard this. We're going to be taking clockwise as positive, right? So this 48 kilonewton now is going in this direction. Taking moment about A. So it's going in this direction. You know that O is moving clockwise, like the hand of a clock. Clock is always like this. The clock now, the ticking hand is always moving like this, like this, like this, like this, like this. So it's always moving like this. So we have this is clockwise, right? That's why I used to remember it. So you have this one going in a clockwise direction. So this is 12 times, that's positive 12. This is 4 plus 2. Sorry, 48 rather. Since 48 times 6. Then we have this 10 also moving in the clockwise direction, plus 10 times, what's length from here to here? 4 plus 4, 8, plus 3, 11. So that's 10 times 11. Then we also have this RBY moving again in this direction. That's in the anti-clockwise direction now. So it will be minus RBY times distance from here to here is 8. Oh, I forgot to put about summation of moment about this point is equal to 0. So after we summed all the moments, it will be equal to 0. So let's go on to solve. This will be 288 plus 110 minus 8RBY is equal to 0. It's always important to solve stepwisely so that you don't miss either the sign or your calculation. So RBY will now be equal to, okay, minus 8RBY will be equal to minus 398. So R minus will cancel, minus RBY will be equal to 398 over 8 kilonewton. So RBY will be 49.75, right? So quickly, summation f of y is equal to 0. So all the forces in the vertical direction, we're going to add everything together. This is in the vertical direction, so RAY going up. See, to know the sign, you have your graph. This is positive, this is negative, this is positive, this is negative. So depending on where the arrow is pointing to, the arrow is pointing down, negative. The arrow is pointing up, is positive. The arrow is pointing this way, is positive. The arrow is pointing this way, is negative. So we have RAY pointing upward, which is positive, plus RBY pointing upward, which is positive. RBY, right? Then we have 10 going down, minus 10. Minus, remember we converted this to a point load. So this will be minus 48 kilonewton. So RBY, RAY plus, we calculated RBY is 49.75, so we substitute 49.75 minus 10 minus 48 is equal to 0. So you punch that in your calculator, you make RAY subject to formula, you get 8.25 kilonewton. So quickly, you will now take an elemental portion of the beam. So we want to start sectioning the beam. We're going to be sectioning the beam to know what are the conditions at every point in the beam, at every loading. Okay, in this place that there's no load now, what is the condition? When there's load, what is the condition? After the load, what is the condition? So definitely, to know where you are going to section, you are going to be able to look at the diagram and know that, okay, if it's a free beam, there's only one condition that you can have. But since this load has come now, the condition is going to be different. So you know that the condition here is different from the condition here. So you know that you call this place, we are sectioning this place XX. Let's call this X1. You know that the condition here is the same thing as the condition here because there's no load that is being applied. So you section it here again, X2, X2. You know that the condition here has changed. So after the load, you see section it again, X3, X3. So you know that the condition here too has changed. You cannot section this place because it is outside of the beam. So you are going to always be sectioning within the beam. So you are going to section the beam 1, 2, 3 times. So let's take the first side for instance. So we are going to, okay, let's do our summation fx, summation f of x, pointing in this direction. So RAX positive is equal to, there's no other one pointing in that direction, so is equal to 0. So taking an elemental portion, let's take this portion, x1, x1. So we have this point load, calculated RAY to be 8.25, right? Going down, Vx, next. So when you cut the load, there will be an imaginary force pulling the beam downwards and also a moment acting.
Okay, so these are some trial questions I want us to try out.
Vx and then this
Having
moment
solved a
It is
few
always, anytime you
examples,
section a beam,
please
this
try
would
and
always be
solve them.
found.
They're actually pretty
So
easy. Thanks for
this unknown will
watching.
help us know
See you
the
next
moment
time.
at this point and
Bye.
at this point, and the shear force at this point. So this place is going to be x, right? So, and how do we know where our x will range from? So you know that before this UDL, your x is ranging from, it's just 4. Your x is 4. So 0 is greater than or equal to x. and x is less than or equal to 4. So you know that your x is from 0 to 4. 0 is greater than x, right? And x is less than or equal to 4. So any x that you pick has to be greater than 0 and also has to be less than 4. So you have x ranging from 0, comma 1, comma 2, comma 3, comma 4. 0 is satisfies 0 because if x is 0, x is either less 0 is either less than x or equal to x. If x is 1, 1 is greater than 0. If x is 4, it is also x is also less than or equal to 4, so it's also equal. So we have these are the range of our x. I'm just trying to explain what these signs mean. So moving on, we're now going to do the same thing, the same idea that we used here. We take moment about the side that is being sectioned, x1, x1. So taking moment about x. Sorry, I'm not writing it completely. So summation mx will be equal to 0, while clockwise moments are positive. So let's look at this mx. This mx now is moving in the clockwise direction. So that's mx positive. Then don't mistake this vx as part of the moment that you're calculating for. No, you're not meant to do that. Remember, I said that every force acting from the point in which you're taking moment from is always 0. So this vx doesn't exist here. Then you now have this 8.25. So this 8.25 is coming all the way here. It is in the clockwise or anti-clockwise direction. It's in the clockwise direction plus 8.25x, right? Which is equal to 0. So mx is equal to minus 8.25x. So we have when x is equal to 0, mx will definitely be equal to 0, right? Because if you plug in x here as 0, this times will be 0. So when x will be equal to 2, mx will be equal to what? So let's plug it in our calculator. So 8.25 times 2, that's 16.5. It's been minus 16.5. So let's just use this space here. When mx is now equal to what? 4. When x is equal to 4, mx will be equal to what? 33 minus 33 kilonewton per meter. Let's not forget the units, right? So let's do for our v of x now. So you do summation f of y again. Summation f of y, basically the same thing you did to calculate the reactions. So summation f of y is equal to 0, where upward forces are positive. You have this going up, which is positive 8.25. And then you have Vx going down, minus Vx is equal to 0. Minus Vx is equal to, goes to the other side, becomes negative, minus 8.25. Negative cancel negative. So Vx is equal to 8.25 kilonewton. That's for the first section of our beam. Alright, so let's continue. So taking the other portion of the beam, we're on a new page. It is going to be this way. Now we have here R A Y, which is equal to 8.25. Then we also have a UDL. We cut half of that UDL, a portion of it. We don't know the portion of it, but we are going to find out Vx, Mx. So I want to say it's always important that you don't change, as long as you are going from the left side to the right side, you don't always change. You never change the position of your Mx. Alright, so we have this as 12, we have this as x, and we have this as 4, right? So let's take a moment about this side that we cut, that is x. This is, don't forget, this is x2, x2. So we have this going in what direction? Clockwise direction. So 8.25 times this from here to here is what? 4. 4 plus x to get the distance. We now have this 12 kilonewton. Remember that we cut it. So this one that we use as 48 point load is not going to be 48 anymore. We'll now take another area. So 12 times x, that should be the new area. That is 12x. Going also in what direction? In the anti-clockwise direction. Minus 12x. So you know that the position of it will be in the middle of this, the point load. So where's the middle of this? To get the middle of this, that's x divided by 2. So we now do times x over 2. Don't forget your moment. Your moment is moving in the clockwise direction. Plus mx equals to 0. So quickly, we are just going to simplify. This becomes 8. This times this is 8.25x plus 33, right? This one cancel this to become 6x raised to power 2 plus 33. Okay, we already put it 33 plus mx equals to 0. So our moment equation mx will be equal to 6x squared minus 8.25x minus 33. So at x equals to 0, one thing I want you to notice that, you know the previous one that we did, from here to here, the maximum length was 4. And the maximum length we got here was what? We got minus 33 kilonewton, right? So if x here, this x now, is now 0, it means that whatever we get here and what is here from the equation has to be equal. What do I mean? Your final answer here at this longest length has to be equal to what you get when this place is 0. Because when this place is 0, this place is 4. I don't know if you get what I'm saying. Nothing has changed. So your final answer has to be your first answer in your moment equation. What do I mean? So if you put mx, when at x equal to 0, mx will be equal to this. If this is 0, this is 0. If this is 0, this is 0. Mx will be equal to minus 33 kilonewton per meter square. Per meter. So you realize that it was the same thing because when x was 4, because x is 0 here. Do you get? So at x equal to, the maximum length of this one now is 4. That's 0 greater than or equal to x less than or equal to 4. So your x is in between from 0 to 4. And we've done for 0. Let's do for 4. The third one is going to be like this. We have our RBY, which was 49.75, 8.25. Our EDL 12, METF 4. Don't mind my handwriting. I know my handwriting is not fine. KTS 3 kilonewton per meter, 10 kilonewton. So let's not forget our Vx, right? And let's not forget our moment mx. So one thing I want to show us is that for ease, right? For ease, instead of going through all this process, you know, we have the other end of our beam that is like this. Then I don't want to confuse us. X, right? This will be x. Sorry, this will not be 3. This will be x because we are cutting it before the 10 kilonewton load. Sorry, I'm so sorry for this mistake. We are cutting it before the 10 kilonewton load. So this will be x. We don't know what this distance is. And then this is like the other half, right? So you can decide this will not be Vx, Mx. You can decide that you want to use this one. You can decide that you want to use this one. But know that if you are going to use this other side, so that you don't go through all this process, there has to be a change in the direction of your moment, because you can't put it in the same direction because you are taking the opposite side now. So the opposite side has to have an opposite moment. So we see that this one is going in the clockwise direction. This one is going in the anti-clockwise direction. So even if the same way you did this one, the same way you do this one, because when you take moment about x, this is going in what direction? Clockwise. This is going in anti-clockwise. This is also going in clockwise, right? So when you do x at x equals to 0, you can try it out. At x equals to 0 here, has to be the final answer that you got here, 30 kilonewton, right? So I'm just going to be looking at this side. That's how you can be sure that you are in check. So if I'm paying attention to this side just to save time, mx is moving in anti-clockwise direction minus mx plus 10 is moving in what? In the clockwise direction. So 10 times x. 10x is equal to 0. Can you see how easy it is? So you are sure that minus mx is equal to minus 10x, right? Mx will be equal to 10x. So you know that when x is equal to 0, m will be equal to 0. That is here. So you're not counting from here like this, you're counting like this. So when x is 0 here, this is what you get. So when x is now equal to, you have 0 greater than or equal to x less than or equal to 3. So you have from 0 to 3 because that is the length in the beam they give us. So when x equal to 3, our mx is equal to what? 30 kilonewtons. How do I know I'm right? Because when mx is equal to 3, that's at this point, right? That is where it met with this one. I don't know if you understand what I'm saying, and that is what we got as our final answer here, 30 kilonewtons. Let me draw the diagram again so that it is very clear. Let's say this is our RA, this is our RB, and then this is our 10. Then this is our point load, and then this is 4, this is 3, this is 4. So what am I saying? What I'm saying is that when we got 30 here, that has s equal to 3. We're going like this. This is the 3 here, right? And this place, when we did it here, x was equal to, rather, x was equal to what? 4. That is when x is equal to 4. Where is it? Let me find it. At x equal to 4. At x equal to 4, that is this point, right? 30. So I know that where these two meet, that is this place and this place. I'm meant to get the same thing either ways. So if you do it this way, right? If you do it using this diagram, at your x equal to 0 here, x equal to 0 here, you're meant to get what you get as x equal to 4, which is 30. And then your final answer here, your moment equation is also always meant to be equal to 0 at the end of the beam. So at the end of the beam, your moment equation is always equal to 0. So you know that the end of the beam, according to this diagram, was as x equal to 0, and x equal to 0, mx is equal to 0. So let's go on to the shear force and the bending moment diagram. Alright, so for the shear force and the bending moment, we have a reaction going upward on this side by 8.25. I'll just draw this here. So we're going to go up by 8.25, positive 8.25, right? When we calculated our Vx at x equal to 4 is 8.25, so it goes, because there's no loading here, so the force doesn't change. We encounter a loading at this point, so definitely something has to change. 0. This is 8.25, right? So we now calculated that Vx as x equal to 8. That here is 4 and here 4. So definitely this point is 8. That is this point. That's minus 39.75. So it's going to go up from the positive side to the negative side. Minus 39.75. We have a reaction here to going upwards. So it goes upwards. It goes upward by 49.75. So minus 39.75 plus 49.75. So that's just 10. So it goes up by another 10. 10 should be somewhere here. Maybe. It's not to scale, but then this is how it will look like. So 10, you have 10 here. So there's no loading here. We also calculate when we now got here, there's also a point load taking it down. This is 0. This is what? This is 10. As easy as that. Then for the bending moment diagram, I already took out what we got. So you can just cross check. So this is 0. At x equals 0, mx equals 0. So we start from the 0 point. At x equal to 4, mx is equal to minus 33. So from here to here is 4. You know that it's going down the negative direction. So this place is minus. Let's call this minus 33. And then at x equal to 8, this is 0.8. It is down 30. That means it has moved up to 30, right? To the curve. And at this 30, it goes straight down. What's the point? Look. Then at x equals to 11, mx equals 0. So basically that's it. Then you will now put negative, positive, VE, positive. Can shade it. Can shade it. Then this one, just put negative, positive, shear force diagram, bending moment diagram. Please, when you are drawing, use ruler. Draw everything as possible. All the details, the distance, the length. Putting this is 33. This is 30. This is 30. Minus 30, positive 30, as such, and so on and so forth. I guess that's all.